Hey everyone, today we're diving into a discovery that nobody, absolutely nobody, expected to see at this stage of the 3I Atlas journey. For months, this interstellar object has challenged everything we thought we understood about comet behavior. But the latest observation doesn't just add another anomaly. It tears open a completely new chapter that forces scientists to reconsider some of the most fundamental assumptions in cometary physics. 2 nights ago, an amateur observatory in southern Chile captured an image that immediately sparked debate across the astronomical community. At first glance, it looked like a normal post-perihelion capture, a dimming nucleus, a fading coma, and the remnants of a standard dust tail stretching away from the Sunday. But as researchers began sharpening the raw data, something unexpected emerged from the noise. So unexpected that several astronomers initially thought it was an optical artifact. A dark, razor-straight filament appeared to rise from the nucleus, pointing not away from the sun, but perpendicular to the sun's direction. A thin vertical column, almost like a jet of shadow, stood out sharply against the surrounding glow of the coma. And at the same time, 2 broad horizontal features, one bright, one faint, extended on opposite sides of the nucleus. 3 structures, perfectly arranged at 90-degree angles, appearing simultaneously in a configuration no one had ever documented before. Within hours, observatories in Argentina, Australia, and South Africa reported seeing the same structure. This wasn't a glitch. This wasn't a processing error. This was real. 3I Atlas had revealed a new, rigid-looking geometry that defied every model describing how dust and charged particles should behave around a natural comet. To understand why this discovery sent shockwaves through the scientific community, we need to revisit how cometary structures normally form. A typical comet produces 2 primary tails, a plasma tail and a dust tail. The plasma tail, shaped by the solar wind, is usually straight, narrow, and bluish. The dust tail is broader, curved, pushed gently outward by solar radiation pressure. These 2 features behave predictably. They rotate, fade, and deform according to well-studied interactions between sunlight, dust grains, and magnetic fields. But nothing in standard comet physics produces a rigid vertical structure, one that appears to rise from the nucleus like a beam locked in place. And nothing produces a symmetric pair of horizontal outflows that maintain shape despite the turbulent forces acting on an active interstellar object. Scientists began calling this new formation the cross structure, although many admitted the term doesn't capture the complexity of what they're seeing. Because when the images are examined in detail, the vertical feature isn't simply a column of dust. It's darker than the surrounding coma, as if something inside the nucleus is blocking or absorbing reflected light. Some researchers even suggest that the structure resembles a shadow, though a shadow requires an object and a surface to cast upon, neither of which exist in the empty vacuum around a comet. The 2 horizontal features add to the confusion. One appears denser and more luminous, spreading outward like a dust ribbon rich in reflective particles. The other is thin, faint, and sharply defined, consistent with a fast-moving ion stream. But both originate from regions of the nucleus that should not, under normal circumstances, produce stable jets pointing in opposite directions at perfect symmetry. As the scientific world scrambled to understand these bizarre structures, Harvard astrophysicist Avi Loeb published a brief note summarizing the early data. He didn't attempt to explain the origin of the cross pattern. Instead, he emphasized that 3I Atlas continues to behave in ways that challenge our models. He pointed out that many comet jets rotate with the nucleus, Yet this formation appears locked, unaffected by any observable rotation. He also noted that the vertical feature's stability suggests either extremely large particles or an ejection mechanism unlike any previously recorded in natural comets. This new geometry has raised several questions that researchers are now racing to answer. First, what is the vertical structure made of? If it consists of large dust grains, they must be massive enough to resist solar radiation pressure and remain aligned for days at a time. But the volume of such grains needed to create a visible, persistent column would be enormous. Second, how are the two horizontal features being produced without dispersing? Natural comet jets scatter quickly unless their source regions are remarkably stable. Yet in these images, the horizontal streams look almost engineered smooth, evenly distributed, and perfectly balanced. Third, why does the entire structure appear so coherent, as if following a hidden framework? To explore the possibilities, scientists have begun modeling three primary scenarios. The first is the large grain scenario, where massive particulate matter is released in quantities far beyond what a comet should produce. This may explain the dark vertical feature if the grains absorb light strongly. But it doesn't explain the symmetry. The second scenario proposes fracturing events inside the nucleus, causing multiple vents to open simultaneously in fixed orientations. These vents could, in theory, create stable jets. But it remains unclear how fractures could align at perfect 90-degree angles. The third scenario is the most debated: a directed outflow governed by internal structures, channels, cavities, or magnetic alignments that act like fixed nozzles. This explanation does not imply anything artificial. Yet, even as a natural model, it requires a level of internal order that scientists have never observed in comet nuclei before. Our understanding of 3I Atlas has already been stretched by its previous behavior jets that did not rotate with the nucleus non-gravitational acceleration inconsistent with mass loss, and a nucleus far more resilient than early predictions suggested. The cross structure adds yet another item to a growing list of anomalies that make this object unique among interstellar visitors. And this is only the beginning. In the next section, we're going to dive deeper into the physics behind this new formation, examine what current models predict, and explore what astronomers are expecting to observe in the coming weeks as Atlas continues its journey. To understand what this new cross-shaped formation might reveal about 3I Atlas, astronomers have turned their attention to the behavior of cometary material under extreme conditions. When the Chile images were cross-referenced with data from Australia and Argentina, researchers noticed something even more unusual. The vertical structure did not simply point upward relative to the sun, it maintained its orientation relative to the background stars. That means it wasn't drifting, bending, or dispersing like an ordinary dust jet. It held its position as if anchored to a rigid axis. This observation shook even the most cautious scientists, because it implies a level of internal stability that comets, by their chaotic nature, don't possess. Comet nuclei are fragile, porous, constantly disintegrating bodies. Their jets are the product of uneven heating and random internal fractures, not precision or symmetry. Yet here, in the data, is a structure that behaves more like a standing pillar than a plume of escaping dust. Researchers began to question whether the vertical feature might be composed of very dense particles, so dense that sunlight barely influences them. But if that were the case, the structure should still disperse over time, as gravitational interactions and micro-collisions within the coma gradually push the particles apart. Instead, the feature remains narrow, dark, and sharply outlined. Some astronomers even suggested it might be composed of mineral fragments not typically found in icy bodies, fragments that could have originated in an environment very different from our solar system. The two horizontal features raise even more questions. The bright horizontal stream exhibits brightness fluctuations that match no known dust behavior. The fluctuations are rhythmic, almost pulsed, appearing at intervals of several minutes. Dust jets do not pulse. They fluctuate irregularly, tied to chaotic changes in surface heating. The faint horizontal stream, on the other hand, behaves like an ion tail, fast-moving, electrically charged, and sharply defined. But ion tails are pushed directly away from the sundae. This one points sideways, maintaining a stable trajectory independent of solar wind direction. When combined, these three components form an arrangement so geometrically precise that researchers compared it to dynamical simulations of magnetic field interactions, even though no comet has ever shown this kind of behavior. Some suggested that the vertical feature could be aligned with an internal magnetic axis, one that remained stable as the nucleus rotated. But this hypothesis faces a major challenge. Comets are not known to have strong internal magnetic fields. In fact, measurements from Rosetta at Comet 67P showed the nucleus had virtually no magnetic field at all. The more scientists try to interpret the structure within existing frameworks, the more contradictions emerge. One model predicts the vertical feature should fade quickly. Another predicts the horizontal jets should wobble. A third model suggests the entire pattern should rotate along with the nucleus. Yet none of these predictions match what's being observed. This has led several researchers to propose that Atlas may possess internal cavities, tunnels, or crystalline regions that channel material in fixed directions. If the nucleus was formed in an environment with extreme temperature gradients or in the presence of strong magnetic forces, these internal structures could have solidified into rigid pathways for degassing. As Atlas heats up during perihelion and cools afterward, gases trapped deep inside could escape through these channels, producing the stable geometry now seen. But even this hypothesis doesn't fully explain the dark vertical structure. If it were produced by outflowing material, it should scatter sunlight or emit faint ionization signatures. Instead, it absorbs light. In one frame captured in Argentina, the structure appears as a silhouette black against the luminous coma. A silhouette requires something blocking the light, not emitting or reflecting it. This has led to speculation that the vertical feature may not be made of material escaping the nucleus at all. Instead, it could be an absence of material, an evacuated channel created by unknown internal processes. In simpler terms, it could be a shadow-like void inside the comet's own coma. As this debate grows, attention has shifted to the rotation of 3I, Atlas. Based on earlier light curve measurements, the nucleus rotates slowly, completing a full rotation in just under 17 hours. If the cross formation were tied to the surface or a set of jets fixed on the nucleus, its orientation would shift over time. But images from across 3 continents show the structure maintaining the same alignment throughout the entire night. The orientation only shifts with Earth's perspective, not with the comet's rotation. This is one of the most confounding aspects of the discovery. The geometry behaves as if it is external to the rotation of the nucleus, yet anchored to the nucleus at the same time. It rotates only with Earth's sky, not with the comet itself. To investigate this further, astronomers are now focusing on spectroscopic analysis. By observing the wavelengths emitted or absorbed by the vertical and horizontal structures, They hope to determine their composition and velocity. If the vertical feature is indeed an evacuated region, spectroscopy should reveal a lower concentration of particles compared to the surrounding coma. If it consists of mineral fragments, it should produce distinct signatures absent in the dust tail. Meanwhile, the horizontal structures will be examined for plasma signatures. If the faint horizontal jet truly is an ion stream, it should emit light at wavelengths corresponding to ionized carbon, nitrogen, or oxygen. But the sideways orientation remains a puzzle. Solar wind simply does not push ionized particles in lateral directions unless there is an external force or field influencing them. Researchers have also begun analyzing how sunlight scatters off the structures at different angles. This will help determine particle size, distribution, and density. Large particles scatter light differently from small dust grains, and these patterns can reveal hidden details about the internal behavior of the nucleus. As the comet approaches its closest point to Earth in mid-December, observatories around the world will have their best opportunity to study the cross formation. Telescopes in Hawaii, Spain, and Chile are preparing for coordinated observation campaigns, capturing the comet at multiple angles simultaneously. This will allow scientists to determine whether the structure is truly three-dimensional or only appears so due to projection effects. But the early data suggests that the geometry is real. The vertical feature appears to extend hundreds of kilometers above the comet, while the horizontal features stretch outward for thousands of kilometers. This scale and stability are unlike anything previously recorded. While the scientific community works to decode these observations, the broader significance of the discovery begins to take shape. ATLAS has already defied expectations with its durability, unusual tail structures, and unexplained acceleration. The cross formation may be a clue, a window into the internal complexity of an interstellar body formed in an environment radically different from our own. In the final section, we'll explore what the coming weeks may reveal, what scientists expect and fear to find, and how this mysterious structure may reshape our understanding of interstellar objects entirely. As we move into the final stretch of this unfolding mystery, astronomers around the world are preparing for what could be the most revealing period in the study of 3I Atlas. With the comet drawing closer to Earth day by day, every new observation becomes a piece of a larger puzzle, one that could redefine how we interpret the behavior of interstellar visitors. And now, with the emergence of the cross-shaped structure, that puzzle has become far more intricate than anyone anticipated. One of the key questions scientists hope to answer is whether the formation is temporary or permanent. Many natural comet features, jets, plumes, asymmetries come and go as the nucleus heats unevenly. But the stability of this geometry suggests something different, something enduring. If the structure begins to shift, fade, or distort as Atlas approaches its closest point to Earth, that could indicate a natural mechanism gradually losing strength. But if the structure persists with the same precision and alignment, it may point toward a deeper internal organization within the nucleus. To capture these changes, observatories are planning synchronized tracking sessions that follow the comet across the entire night sky. By stitching together footage from locations separated by thousands of miles, scientists hope to reconstruct the three-dimensional architecture of the structure and track its evolution over time. This kind of multi-longitude observation has been invaluable in the past. But with Atlas, the stakes feel higher. Every shift, every pulse of brightness, every subtle change in shape could offer critical insight into the forces driving this phenomenon. Another major focus is the internal rotation of Atlas. If the nucleus rotates unevenly, like a tumbling asteroid, Internal stresses could create periodic changes in the jets that feed the horizontal features. But so far, the cross formation appears unaffected by such motion. As the comet rotates, the shape remains fixed relative to the background stars, shifting only with the changing angle of Earth's view. This raises the possibility that the internal structure of the nucleus is not homogeneous. It might contain regions of anomalously strong cohesion, perhaps shaped long ago in the primordial environment of its home system. These regions could guide outflows in ways no solar system comet has ever been known to do. As observations intensify, some researchers have begun modeling the potential effects of exotic ices trapped deep within the nucleus. In extreme cold environments beyond the outer edges of planetary disks, unusual compounds such as nitrogen hydrates, carbon allotropes, or metal organic complexes could form stable crystalline structures. If these materials were heated during Atlas's passage near the Sun, the resulting gas flows might be funneled along well-defined pathways, creating the strange geometric precision now seen. But while this theory predicts structured outflows, it does not explain the darkness of the vertical feature. If the column were composed of outflowing material, it should reflect at least some sunlight. Instead, it remains stubbornly dark, even when enhanced with the strongest filters. To investigate this anomaly, astronomers are beginning to look beyond traditional comet physics. Some have suggested that the dark column may be the result of low-density plasma or an ion-depleted cavity forming inside the coma. Others propose that the structure could be a region of destructive interference, where electromagnetic fields reduce the density of charged particles. One hypothesis gaining traction is that Atlas may have interacted with a strong magnetic environment before entering our solar system, leaving it with residual magnetization along a particular axis. If internal pockets of ionized gas respond to this lingering magnetic alignment, the result could be a stable, vertically oriented channel within the coma. But this requires assumptions about the comet's past environment that are difficult to verify. Meanwhile, the horizontal features continue to raise questions of their own. The faint, fast-moving stream appears to accelerate over time, suggesting that it may be interacting with solar wind in an unusual way. The stronger, brighter stream shows intermittent waves along its length patterns that seem to ripple outward like vibrations traveling through a flexible structure. These waves may indicate varying intensities of gas release from the nucleus, hinting at a pulsing internal process that has not yet been fully identified. As scientists debate these theories, one thing is clear: the cross formation is not a simple optical illusion. It is a real physical configuration shaped by forces that are still poorly understood. And as Atlas moves farther from the Sun, these forces may become more pronounced, not less. Interstellar objects like Atlas often behave differently on their outbound trajectory, as their internal ices resolidify and trapped gases repressurize. This phase can produce unexpected flares, jets, or structural changes. The cross configuration may evolve in ways that reveal its true nature. The most anticipated observations will occur in the final days leading to the comet's closest approach. Radio telescopes will attempt to detect fluctuations in ionization levels around the vertical feature. Optical telescopes will study the edges of the horizontal streams, searching for breaks or turbulence. Space-based observatories, including several that have remained silent until now, may release new data about the comet's thermal profile and composition. If Atlas follows the pattern seen with previous anomalies, the days before closest approach could bring sudden shifts. This happened with its unexpectedly stable sun-facing jet. Its momentary halt in motion observed weeks ago, and its unexplained non-gravitational acceleration. Atlas has a habit of revealing its most baffling behavior precisely when scientists think they are beginning to understand it. And so, the astronomical community waits, watching, preparing. Every night brings new data, new questions, and occasionally quiet moments of awe. Because beyond the scientific implications, there is something profoundly moving about witnessing an interstellar visitor behave in ways no comet ever has. It reminds us how little we truly know about the vast spaces between the stars and how extraordinary it is to glimpse even a fragment of that unknown. In the end, the cross structure may prove to be the key to understanding the mysterious interior of Atlas. It may point to exotic ices, ancient magnetic fields, or internal fractures shaped by forces from another stellar system. Or it may reveal something entirely new, something that forces us to rewrite more than just comet physics. What happens next will depend on what the world's observatories capture in the coming weeks. Whether the vertical feature holds, whether the horizontal streams widen or collapse, whether new structures emerge or old ones vanish, all of it will shape the emerging story of Atlas. For now, one thing is certain: the saga is far from over. And as this object continues its journey out of the inner solar system, it leaves behind questions that will fuel research, debate, and imagination for years to come. Thank you for joining this deep exploration into one of the most puzzling phenomena we've ever observed. If you want to follow every new development, stay tuned, because with Atlas, there is always another surprise just over the horizon.